Swayam Prabha. Digital India. Educated India.
Okay, good afternoon. So we are on to the geosequestration part of it. And since most of you are chemical engineers, everything but earth scientists, I thought we'll do a crash course on what properties we use and how we determine them. So bear with me as we go through just one quick thing on what properties we use, how do we measure them, and then how do we use them for carbon sequestration. That will be our topics for today. Most probably I'll change this a little bit around, but for now this is the sequence for today for this segment of geosystems and geostorage. So first of all, where do we store, right? We've been talking about formations and we've said we have different types of formations. So what are the properties of geologic formations that make them useful for large scale storage? We're not talking about storage in tons or kilotons. We're talking about storage in millions of tons. So what do we need? And at some point, we'll discuss what are the potential storage targets in India, either in the sequence of these 4 lectures or the 2 following that, so that we look at the logistics, but look at the logistics in a geographic sense. It doesn't help you to look at formations in the North Sea or in US, because that's not what you have here. There are analogs and you can use those analogs, but we'll talk about what type of formations might be existing in India. Okay, so before we go anywhere, what are the basic concepts? How do we know? We are determining what's below our feet, right? What's below the surface. So we have, if you think of the mouse as my sensor, we have one way of moving things around, and you can see that there is movement here. So depending on whether I can move through or I have to go through the point here, we use this guy. So I'm standing over here and I want to know what formations are here. I want to know if there is any fault over here, and I want to know if there is any structure coming here, and I want to also know what is, if this is my target, I want to know what the storage capacity is here. Okay, all I have is standing over here, right? So I can make measurements along the surface here. This is what I do when I move my mouse on this desk here. That's all the information I have, right? So whatever sensor I put in has to penetrate through all of these formations and go here. If this is my target here, then I need to know what is the porosity here, and what is the stiffness, and what is the permeability. Now, none of the tools that we use on the surface here will give me this information. So what we do is we make measurements and we make models. Those models relate what I measure here. So that's my observable with my parameter needs. So I have observables, so I have needs, and I get to use my observables with models to get to what I really need to be able to store. So one is surface measurements. The second one is to drill a well. So I can drill a well that goes till here. And now what I'm doing is I'm lowering tools to stay with this analog. If I've drilled a well, I think it goes in here, that's my tool. I'm lowering it down It's going all the way down and I'm pulling it back up. As I'm pulling it back up, I'm measuring. This can be as simple as a camera, optical camera, so making images of what the thing looks like, what the formation look like, or I can be doing more complex measurements that will give me porosity, stiffness, fluid content, saturation of fluids, and so on. So what we will look at today, that's the part that's the work that we do in geoscience. We make some measurements either on the surface, or we drill a well and we make measurements, and then we use models to invert properties that we need from those models. So we'll look at some of the definitions of properties, we'll look at some of the models. We'll see how we create porosity maps given what we have from the surface. What are the uncertainties and what are the challenges in using models? One of the biggest challenges that we face in geophysics is to determine saturation. None of the logs that we use give us saturation. None of this surface tools that we use give us saturation. We have some direct measurement or indirect, but more direct than seismic. We have some way of getting porosity from well logs, from the wells we drill. But if we are measuring at the surface, most of the times we use seismic data. Those models are very crude. So the two major parameters that we need, saturation and porosity, are not as well defined as we would like them to be. Okay, so what are these? What are the types of information that we need to be able to do the job? We make measurements at many different scales. We are going from a field scale, this is in the field, to a pore scale. These are thin sections, SEM images, very high resolution images. They can be on the order of microns, nowadays nanometer scale. We can image everything very well. If we go higher up, we have borehole images, ultrasonic images, reflections. We can analyze those. We get from micrometer scale to a centimeter to a millimeter scale. In here, we also have core images and core measurements. So we have anywhere from centimeters to meters. If we use wireline logs, that's the wells that we drill and we put these sensors in the subsurface, we get resolutions of tens of meters depending on the tool that we use. We can have higher resolution, we can have lower resolution, but usually it's on the meter, tens of meter scale. This is from the top of the surface. This is absolute measurement, the resolution what we have. So here, for example, that's the wavelength. Yes. So we use wireline logs, for example, to get thicknesses. So we can say, and we'll look at one of the examples on how we do that. So we can say, this is my wireline log. I have this as my target, and I can get the thickness of that wireline log. So that is possible. The part that is critical here is to say, we can get information at every scale in size, at every scale in frequency. Reconciling information from this scale all the way up to here is a challenge. Most of the time we'll be required to do that. For example, if we are looking at storage here and the storage is on a pore scale, the storage is trapped in very small pores, we will be measuring it using either thin section images, or we will use some sort of adsorption, desorption curve, isotherms, invert that for pore scale. We will be using something like NMR data, invert those for pore scale. But then once we have that, we want to be able to come over here. If this is my target here, then I want to get this part here analyzed for not only its porosity, not only its stiffness, but also the type of pore structure that might be there. And therein lies the challenge, because I cannot jump from here to there. So we are required to investigate data at different scales in size, small sample, big sample. Typically, your thin section images will be a couple centimeters long, thick. Core scale will be, sorry, not couple centimeters, a couple millimeters. Your core scale information will be from a couple of centimeters, and so on, till you get to hundreds of meters. So we are averaging. We are averaging over all of these properties one scale up. So the challenge then becomes, if I have a pore scale model, that pore scale model needs to now be scaled up. So let's say I have a pore scale model for this part here, and I have a pore scale model for this one here, and for this one. Out here, that might be one piece of information, which means all of these combined will give me one data point here. So I need to have an average model that combines this one, and this one. And we know these models, right? You can take a geometric average, you can take an arithmetic average. Those are simple mixing models. We need something more complex than that. And so we will examine some data and see how do those mixing models relate to what we are trying to do all the way up to here. But what I'd like you to walk away from this class, if you take nothing else away, then it is to say the scale of your measurement matters. Size always matters. We have, for example, if you were to examine this room and we look at I think there's a very famous example of different people looking at an elephant and describing various parts. That's pretty much the job we do. I didn't use that example because it's used everywhere, so it's kind of boring. But it is a good analog. You are trying to describe different parts of a material, and at the end you need to put everything together and come up with what the full information should be for the formation. So mixing models become really interesting. Before we get there, we need to drill a well. So what do? That's our borehole. This is a typical derrick. We have the bore string over here. You have casing. So all of these here, you start with a very big well over here, and then you change out your drill bit, you go to the next one, you put casing, you cement it, you dig the next one, and so on. So in this case, we only have 3 different sizes. This is where you're making the well. This is where you're cutting. So that part is enlarged over here. This is what you've drilled till now. Here's what your drill bit looks like. And this one is pumping mud in the middle, and that mud carries out all of the cuttings. How many of you have drilled a hole in the wall? Okay. How many of you have drilled a hole in the wall and that has become larger and larger than the size that you wanted to drill? Okay. So this is the problem that we face always. This is like drilling a hole in the wall and you have to hold it straight. What happens if you keep drilling and don't clean out the well, the bore? You form powder, it becomes very hard, right? Because you're drilling and you're crushing and it becomes a powder till you can't drill no more. So you have to clean it out, right? You have to ream it out. you need to cool the bit. So you need to cool the bit, you need bring it out, you blow on it, or you do something. And if you're doing cement or concrete drilling, you need to do percussion drilling, and you need to cool it with water, right? All of you who've drilled rocks, you will know you need to cool your blade. So that's pretty much the exact same thing, just put it in the subsurface. You had a question, yes? You need to, so the size, you need to know what type of rock you're going to drill. Yes, absolutely, because you're going to choose your drill bit, right? Your drill bit will be defined by the formation stiffness. So, so when we drill, for example, I've sailed on drilling ships, on ships, and what we've done is you normally, this is then ocean here, let's say this goes all the way, pretend there is no water. On the top you have ocean sediments. Those are very weak. So you will use a rotary drill. So that sort of churns through very quickly. It brings out whatever material there is. But very soon you have to go to a diamond corer that cuts through rocks. So, or nowadays different types of materials that are harder and harder, that cut through the material you need. So
actually, ma'am, like when we move ahead with the tunneling process, so
yeah.
before doing doing tunneling, we collect samples, so that we need to know that what is the strength and what are the type of a soil which is present. So RQT basically like it is a classification method which tells us that what quality of rock
quality determination.
Right? Yes. So it basically tells us that what type of a quality. So do we do that kind of a test over here to determine that what kind of material we are going to find it out?
Yes. So you do. It depends on which field you're in. We call something where it's a mature field. There is a lot of geology that's already been done. You know which one you have. So you do a preliminary study of what you expect to find. If it's a green field, that means there is no information in the area. Then you have no other work to do but to drill it with over-spec drilling design, and then you spec it down. The first well is usually your most expensive one because you don't know what to expect. In the case of tunneling, your job is a little bit easier because it's all outcrop. You have it exposed for the most part. There might be some things which might not be exposed, but the geology is fairly well known. In this case, the geology might be fairly well known, but the stiffnesses are not. So that's the unknown part that we have some uncertainty. For example, over here, this one here. So the shades mean something. So this one is a carbonate formation, right? We don't know. We know that there is carbonate in the area, but we don't know whether we will encounter it here. It could be pinched out, it could be broken up. We don't know if it's continuous. In that case, we will bring corers that allow us to drill through hard rock, but we don't know whether we'll need it or not. So that's the part which, yes, you do have to have some idea of the geology. Without any idea, going out there is foolhardy. You don't want to do that. Oftentimes, we do know what geology to expect. Yeah, sure. The property measurements up front are not possible if you don't have a well. But what we do, you're right, what we do is, before we go out there, we will measure surface information. So we will go out there and get seismic data. We will put usually that, let me just see, maybe we have space here. So you have, this is your surface, and we will put geophones. These are, think of these as putting your ear to the ground, and out here we will have a source that will thump. So that will put in sound waves like this. So what that does is it travels through, and you get reflections and refractions back here. So you get, and you get things coming back. So whatever comes back, you reconstruct what form structure you have. So that's sort of the first piece of information. The second thing what you do is you take all of these data. Now, if I look at this one thing, I will have a wave coming through and then something here, something here. And I can get this one, same thing. And so now I have these information, so I can build my horizon. I said, at the very least, this is what my structure looks like. I have a dipping bed, right? That's one thing. I can take I know the impedance here. So I have impedance information. Let's say I have impedance I1, I2, I3. And this is just the velocity times the density, right? Very much like optics. Think back to your optics. If you have a reflection coming back, let's say if I do a two-way travel time, this thing coming back, the strength of that reflection will depend on the impedance contrast between this zone and that zone. So we are looking at that impedance contrast, and we are defining reflection and transmission coefficients, pretty much like your optical waves where you have your reflection and refraction, right? Exactly the same, slightly more added to it. So these then become the primary pieces of information. We have velocity here and density. We'll get to why we can, yes, you can get impedances, you can map impedances, but you have a product of velocity and impedance. Now, velocity and density. So if you want to have independent information, separate out density from velocity, that becomes a big challenge. Your velocity is your stiffness over density. So your density is going in there twice. So that becomes a challenge. I'm looking for, I really don't care about stiffness. What I care about is, can stiffness, if this is stiffness, this is density, I have this sort of a relationship. Can I get that information here if I have stiffness? And from density, can I get porosity? This is what I'm interested in. I don't care about anything else. And that's the part which becomes a challenge, because I don't have independent information. So you almost need independent information with the density. So the mud that we use here doesn't just stay outside, it invades into the formation. So that makes it a little bit of a challenge, but let's not worry about that, because for the purposes that we want, we are really looking at mud providing us all of this benefits, where we are looking defining borehole stability, maintaining formation pressure. So when we are drilling the well, at some point I had started doing these animations, and this is irritating. So we're drilling through, this is open hole, right? This is pretty much in the wall, we're drilling a well, but the formations we are going through, the material we're going through has fluids of its own. We do not want those fluids to start coming out. So we have this mud at high enough pressure to make sure that nothing flows into the well. We want to keep the fluids in the formation, stay in the formation. So we have a borehole stability. We want to maintain formation pressure. We do not want to have higher pressure in the formation, and that comes into the well bore and blows things out. This is very common in oil wells, because you have oil at a higher pressure. It can happen, it's pretty much you hit a well that is artesian, that has excess pressure, and now you don't have enough pressure in your well, and you're producing the water from another formation. You're cleaning out the well bore, so you're bringing all the material to the surface. This becomes your first information at what is in the subsurface really. This is your ground truth. That's what's giving us the information of what really is there. lubrication and cooling and so on. So there's a bunch of benefits to using drilling muds. We have to use drill muds. There are very rare cases when we do air drilling. Most of the time we'll use drilling muds. Once we have that, we have a log. What we do is well log measurements. This is depth. This is depth, 22,000 feet. Divide by 3 to get, more or less, to get meters, right? So 7,000 meters. For those of you, for none of you who are in G&G, Thunder Horse is a very famous oil field that was discovered 10 years ago. It was a major deal in the Gulf of Mexico. This is the original discovery well. This was by Shell, and it has oil sands more than 300 feet. That means 100 meters of oil. Net to gross, 98%. It's pure. Net to gross is what defines how much of other material do you have in the formation. Almost 98%. So it's almost 100% pure sand. Here in red are where they perforated, out here, a little bit here. And we know that this is a zone because you have, I need to wear my glasses, because you have lithology over here. So this is my lithology. I do not know why it's giving me a very big, but I think we can live with it. So what we have here, this is the lithology. This is just the volume net to gross, how much of shale there is. So if the lines are all the way to the left, that means there's very little shale, there's very little clay minerals present, which means all of this is pure sand, clean sand. Here we have saturation. All these define high saturation of oil. We have compressional velocity here, shear velocity here, neutron porosity out here. So this is in green, neutron porosity, and we have resistivity out here. This is the resistivity we are looking at. So we are defining oil as being very low conductivity material, and so we're using all of these to find out what is in the subsurface. Okay. We can go from here, from the resistivity log, to get saturation via a model. We can use velocity here to get saturation via another model. We can use these two together to get composition. Again, these are model-based assessments. Each one of them will require a certain model to assume and assess and calibrate, and that's when we come with properties of interest. This is compressional velocity, sound waves. This is shear velocity. So this is that a concept? Shear and compressional velocity? Okay. So these are the two differences. If we are looking, shear velocities, as you know, are not sensitive to fluids. So when we compare these two, we get an idea of fluid influence on the rock here. So how do we use geologic data? Obviously geoscientists use them to characterize the basin and so on. Drilling engineers need them for designing mud weights, mud type. Mud type is important because you want to make sure that you don't have swelling clays. Often we'll add something to the muds to make sure that the clays don't start to swell. If you have the wrong type of mud, you can tie up and destroy permeability very quickly. Completions engineers will know where to perforate, what are the storage zones, where would we want to perforate, what are the injectivity in those zones. Reservoir engineers will go through and map the storage capacity, and they will map and a model the extent of the so-called plume. We know it's not a plume anymore, but that is what will be modeled. Finance people will come in and say, okay, how much benefit are we going to get? What are we going to spend? And what is the government going to give us for doing this work? And finally, there will be a landman who will go out and talk with stakeholders, landowners, lessees, bankers to say, this is the prospect we're looking at. Do we have the permits? Who do we ask to get the permits? Who owns the land? How much do they want to lease the land to drill the well? And finally, we will need to inform schools, state and county officials, the mud sellers, the cement factory, the steel factory, banks, etc., so that they're ready for the time when we need the material or the information. Okay. For most of the CO2 wells, we're not using steel anymore because steel corrodes. So we are using Cr chrome 13 and now chrome 25. So this is found to be compromised at monitoring wells. So there have been studies that have said the monitoring well shows us corrosion of chrome 13, and so we need to go to chrome 25. For injection wells, chrome 13 seems to be okay because we are drying them out. Because with the injection of carbon dioxide, everything gets pushed out, and so there is really no water present. If there's no water present, there's no carbonic acid being formed. If there's no carbonic acid being formed, the environment, the aggressive environment doesn't exist. These are new things coming out. This determination is from last year. This year, beginning of this year. And so, as you can see, a lot of things to do it in a way that is long term is still being determined. Okay, so we need rock properties, but we have a lot of controls on rock properties. We have a compositional control, whether we have sandstone or limestone, what sort of porosity do we have, and what type of fluid and what is the saturation of the fluid. So those are compositional controls. We have geometric constraints in the microstructure, in the size, and in the alignment. So we can have heterogeneous structures, we can have anisotropic structures, directional dependent structures. So all our properties will depend on whether we have alignment or not. And then we have time dependent changes where we have compaction just from the overburden, everything lying on top. We have cementation, dissolution, and we have interfacial effects on fluids that are adhering in 1-2 monolayers to the surface that act almost as solids. And so there are effects of these almost diagenetic for most of the cases. And then we have environmental changes, that's pressure, temperature, and fluid pressure, overburden pressure, pore pressure, temperature. Because we are dealing with carbon dioxide, this part here becomes really interesting because we have phase changes going on. And so we are usually trying to be in one phase, in supercritical phase most of the time, for the depth and temperature gradient that we select. Okay, so what are these properties of interest? We have porosity and density. This is what we had in the impedance. We can go from one to the other. It's a very simple calculation, almost trivial. We can, the density is mass per unit volume, porosity is pore to rock volume. Simple stuff, But if we want to go, we usually measure one or the other. If we measure both, we can get a better handle on what fluid and what solids. If we want to go from one to the other, let's say we have density measurement. We need porosity. For that, we need solid density and we need fluid density. If we have porosity measurement, we still need those two other information to convert that into density. Now, it seems trivial, but if you look at the porosity variations, over here we have sandstone porosity, bulk density 2.2. This is a measurement, right? We are using a model to get to porosity. If we think we have a sandstone and we think we have water, pure water, we get a porosity of 27%. If we think we have brine and the density is 1.1 grams per cc, we have an increase for about 2% in porosity. If we have the same fluid but we miss the lithology, again 2% difference. Worst case scenario, we miss the fluid and the rock, we have about 4% variation. Keep those numbers in mind because we will use them for storage capacity. We will compare just a variation between 2% in porosity to see what difference does it make for storage capacity. Okay, how do these fluids reside? This is my rock volume, this is the matrix, very crude depiction, I am not an artist. The blue is all pore space. If I divide them up, then I have the matrix over here, some part of it is shale. We have shale bound water out here, free water here, carbon dioxide, and if we are in a depleted oil and gas reservoir, then we will have oil here. These fluids will be segregated depending on their density. What density do I have? How far do they go? Shale bound water is water that's bound to surfaces and clay minerals. That is not going to move, which is a good thing because every other fluid is going to be movable. I'm just keeping track of where we are. Okay. And so we have a migration of all of these fluids. If we are starting to inject, we are injecting this fluid here. Where it occupies, what level it goes to, will depend on the density contrast between the existing fluids. This is very typical for organic rich shales, but we will need to have saturations, relative saturations of each one of those fluids, which means we need to know the volumes of the fluids and the total porosity of the rock. Okay? This volume we need because we want to know what the mass of fluid is that we can inject. What's the storage capacity? Usually we give storage capacity in weight. Okay, so sources of information, thin sections, visuals, laboratory porosimetry usually as a function of pressure, and open or cased hole wireline logs. All of these give us porosity information. You can also use sonic and you can use resistivity logs, model based. If we use sonic logs, these are seismic information, these are compressional wave data. So if we're using sonic logs, we're measuring travel time of a seismic wave, usually compressional wave, P wave velocity, sound wave velocity through the formation. On the logs, it's shown as 1 over velocity for whatever reason. Well, because it's has numbers that are easier to depict. That is called slowness. Now, travel time, as it turns out, relates to porosity, which is a good thing because we can use that, calibrate it, and use that information to develop porosity maps. To do that, we need lithology and fluid content, and we need a good model. There is a lot of ambiguity, as you might imagine, and so we need more multi-physics information to tie down the ambiguity. If we combine sonic logs, tie them in to seismic, we have the potential to get porosity information for tens of kilometers. Usually the seismic data that we get can be inverted into a porosity cube. Okay, so what does that look like? This is some of the earliest information. This is 1950s, 1960s or 70s. Believe it or not, people still use it despite our complaints and everything, and they use it because it's such a simple explanation. This is travel time. This is porosity. Yes.
Can't we keep your pressurized core samples so that we can get the saturation levels of each fluid?
Say again.
Is it possible to take pressurized core samples, means in situ samples, so that we can get the exact saturation of different fluids?
Yes. Yes, we can, and no, we cannot. Again, it's based on a model. We can do the measurements. We have, and I'll show you experimental data most probably tomorrow or yes, tomorrow in the second half. We can do experimental lab measurements. That's not a problem. As a function of saturation, we can inject, we can calculate how much gas there should be. The challenge comes in when you are out in the field and you have seismic data. Now you need to invert. So you have out here, so you have travel time. This is my seismic information. So this is velocity, right? Travel time. This is my porosity. But my porosity has fraction of water plus fraction of carbon dioxide plus fraction of, let's say, oil. Even if that is not there, I have these two. So the model that I need to make has to partition between these two, and that depends on the velocity of water and velocity of carbon dioxide. So your velocity here becomes velocity V naught, which is without any fluids, plus some gain factor. Gain factor because without any fluids means it's full of air. Full of air, air has a lower velocity than most of the materials, right? So if this is full of air, any fluid that we put in will increase the velocity. So I need a gain factor. So I need almost a gain factor for water. This is water gain factor plus carbon dioxide gain factor. And that's where models come in, because now we need to define how the fluid is distributed. Okay? Okay. Okay. So it is very interesting because the reason these things work is because there is a very large contrast. This is the travel time in most of my rocks, around 40 to 50 microseconds per foot, 3,000 to 5,000 meters per second. Water, carbon dioxide, all these have much lower velocities. So the travel times, this contrast is very large. And so it's one of the reasons why a simple thing of doing porosity dt works. You can get this sort of a relationship where you have at low porosity you have low dt, that's measuring the mineral point, and as you get to higher porosity, this is 100%, this is 0, this is my mineral point, and this is my fluid point. So this is my mineral solid and this is my fluid. Because there is such a large contrast, that model works. The challenge comes in now, we don't really want this model to work as it is. We want to know how is it this for methane, out here for carbon dioxide, here's a mixture, and so on. We want to know this difference here, or for the same porosity, that difference, and then we want to get what's the fraction of water and carbon dioxide. That's really what we are asking the tools to do. This is some work coming from Maxime Lebedev's lab in Australia in CSIRO, and they have measured brine carbon dioxide mixtures. From our lab, we had measured brine carbon dioxide mixtures, but not to the pressures and temperatures that we need today. Our data are older, so they went in, compared their new data to what ours were, and extended that. And so I was very happy to see this. This is brine, and this is brine plus carbon dioxide at a salinity of 10,000 parts per million. And so we see that almost always in this case, carbon dioxide increases the velocity. And so that gives us a very interesting way to understand the distribution of brine saturated with carbon dioxide on where it would go. Okay. I see that it is 5:30, no, 3:30. We should stop here, but we'll come back and look at this information really, this contrast here, this difference is what we will use to investigate. Usually our pressures will be somewhere here. This is deeper formations, these are shallower formations. We will look at these formations to figure out how the fluid mobility will change as we are injecting carbon dioxide into the formation. How fluid distribution will change, how far will one fluid go over the other.